All right, so let's get started. Last time I think we stopped at a very interesting point about kernel methods, and so I want to continue that today. So, all right, so kernel methods. Kernel methods, I think I was trying to motivate kernel methods in one way, and but there are other reasons why we have this whole area of research. But I was trying to motivate it from the in the scenario where your data is not really representable in a d-dimensional space. So that's what I mean when I write it like this. I say, what if X does not belong to you cannot map it into a d-dimensional space, because what we have seen so far for logistic regression, for linear regression, is that we need to compute this W transpose X, which is an inner product between two vectors, right? So if your data is not a vector, then this won't work, right? Then we discuss a little bit about how you can still make it work by extracting D features from your data. Like let's say your data is a string, you can extract D features out of that, or if it's a text document, you can do something. But many times it's not possible or feasible, or it is not a natural way to represent your data, right? And sometimes it so happens that it might be more straightforward to compare two objects. Okay, so there are methods to compare two text documents, or methods to compare two strings or trees, right, or graphs. So what if we have that, right? So then that is what motivates kernel methods, because that similarity function is called a kernel function as well, right? So this is some examples of similarities, but the idea here is that okay, so then we were looking at kernel methods from the perspective of linear regression, and we will look at it in other settings as well. So today let us discuss it from the perspective of linear regression, or ridge regression, which is just regularized linear regression, right? So this is the estimate for ridge regression, right? I'm hoping this is what you're using for your assignment. Of course, if you have done the gradients quiz, this can be something else as well, depending on what your objective function was, right? So you might have different constants in different place, and those will all sometimes trickle inside this bracket as well, right? But this is one standard way to look at it, right? So now, if this is the W that you learned from your training data, remember your training data is your X matrix, that's the input matrix, right? And Y are your training labels. So that's a vector. So if you want to compute the prediction at X star, we typically use this, right? We say Y star is W transpose X star. And then if I replace, so then I can, instead of W, replace this quantity over here. So this is your Y star. What happens is that you can rearrange this formula, okay, using a standard mathematical lemma called Sherman-Morrison-Woodbury formula. Okay, so that lets you sort of rearrange these things. Okay, and in last class I showed you what it is exactly, but I mean that's something we don't have to worry about. The main thing here is that you can rearrange these terms such that suddenly your Y star starts looking like this. So this is different from this, right? Uh, in practice, you wouldn't want to do this. The reason being that if you look at this quantity, right, X is a n cross D matrix, right, and you're multiplying it with another matrix with D cross n. So this quantity inside the bracket is actually n cross n, where n is the number of data examples, right? So if you have to compute your Y star, you will have to invert that large matrix, right? In the original setting, you had to invert the D cross D matrix, which is smaller, right? But this is n cross n. And typically, now D is the number of attributes that you have, n is the number of data points. And in most practical settings, in most realistic settings, n is much larger than D. You typically have many more data points than you have attributes, right? If you're looking at your neural networks assignment, your each data object was in 784 space. So your D was 784 and your N was 60,000, right? So that poses a problem here, but we still go with it because this lets us do the kernel formulation. So I'll show you what that means. Okay. All right. So now we are going to sort of investigate this expression a little more, because it turns out that if you look at this expression, right? So X is your input data, Now your input data occurs in two places. Here, where you're doing XX transpose, and here, where you're doing XX star. So X star is your new data object, right? The one that you're trying to get the prediction on. So now let's look at each one of these, right? So XX transpose, what I'm saying here is looks like this. So I'm going to write it out a little bit. So, so if you write that, so Y star is equal to Y, that's a vector, transpose lambda in. So this is the identity matrix with n entries, plus X, this is your input matrix, and the transpose of that, X, X star, right? So now what is X? X is a n cross D matrix, right? Where each row in X, so this is X, so there are n rows and D columns. Each row denotes a data object. Now there was some discussion on Piazza about the dimensionalities, right? So, and I can see why it becomes a little confusing, because in this notation, what we say is that each row is one data object. But typically what we mean is that this is the transpose of your actual data point. So each X, right, each X1, we always represent it as a d cross 1 vector, right? So this is not x1, this is actually x1 transpose, because it is 1 cross d. Anyway, so the idea is that each row is your data point, right? So now if you are doing x transpose, you're essentially multiplying this matrix, right? So this is my x, and then you're multiplying it with the transpose of this. So transpose will have d rows and n columns, right? So now the output, of course, is going to be an n cross n matrix, a square matrix, and each entry, any entry here, is nothing but taking the corresponding row and the corresponding column, right? Both of them will have the same length, and then you take a dot product of that, right? Because let's say this is ijth entry, right? So this is nothing but xi, which is this vector transpose xj, right? Because you're that's how the matrix multiplication works. You take the ith row, multiply it with the jth column, and sum it up, right? So so in sometimes in machine learning we also denote a inner product, or we call this a dot product or an inner product, right? That's the same. And sometimes we also write it like this. Okay. So essentially what ends up happening is that each entry in this XX transpose is an inner product between every pair of data objects, okay? And then if you also look at this entry over here, this is X star, excuse me. Okay, so this is XX star, right? So XX star is you're multiplying this matrix with one vector. So this is your X star matrix. This is your X, sorry, n cross D. And then you're multiplying it with one X star, which is just D cross 1. So you're going to multiply this with this, that gives you 1. So this is going to be an n length vector. And each entry here is essentially the dot product between any row and this column, right? So each entry here can also be thought of as a dot product between xi, the ith entry, and your x star, right? So the main point that I want to draw your attention to is that in this whole giant expression, all the x's are always coming in as dot products, right? You don't need your x in any other place. All you need is a dot product, right? So let's say it so happens that in your data set, you don't have access to x, okay? All you have is a function d, which you provide x1 and any pair of xi's and it gives you the dot product of those. You can still do your linear regression with that, right? Because you don't really need your x's, right? So let's say you write a function, you write a program, right, in your assignment, and I say that I'm not going to give you the data set at all. All I'm going to give you is a function, and the function you provide it the entry. You just say, give me the inner product between element I and element j, and it just gives you that. So if I give you that, you would still be able to work out your linear regression, because in linear regression you don't really have to know what your input data is. You just need to know what is their inner product. All right, so that is the first point that I want you to understand. The second point is that if you look at this, right, you think of a dot product. So a dot product is some kind of a similarity measurement between a pair of objects, right? So if we go back to our geometry, if I have two vectors A and B, right? Let's say these are two vectors. Then the dot product can also be written as, so when we say A dot B, that's typically written as the mod of A mod of B cos theta, right? Where theta is the angle between those vectors, right? So if two vectors, so in this dimension space, this is A, this is B, this is theta, right? So A dot B is basically the AB cos theta. So if two vectors are aligned, right, then this value will be smaller, right? And if they are far away, then this value will be larger. So you can think of the dot product as a kind of a similarity measurement. It's also known as the cosine similarity. Cosine similarity is the similarity between two vectors, right? So essentially what is happening here is that this inner product is giving you some similarity, right? So keep that in mind, because that's what is going to motivate our notion of a kernel. Okay. So now let us move on. Let us move on to the next setting, where we say polynomial expansion, right? So we have talked about polynomial expansion, and you are doing it in your problem number 5, where I give you some x, right? But then you replace it by a list of functions. So I say replace it by this phi3x and so on, some p functions, right? So in your case, for example, what you're doing is you're replacing x by x to the power 0, x power 1, x squared, all the way to x power p, right? So each one of these is like a function. Now this could be something else as well. It doesn't have to be just polynomial. This could have been sine of x, cos of x, log of x, anything, right? So in polynomial expansion, then what happens? So you can think of the data now looking like a sequence, right? So then your data matrix, remember your x, instead of x, it becomes an uppercase phi. Okay, so phi will be a n cross p matrix. So this one, of course, was n cross d matrix because this was your original data. The phi will be n cross p matrix, and each row in phi, this is easy to understand. So each row in phi is essentially corresponding to this expansion. You take the ith or any object in x, and then you apply all these polynomial functions, and you get this new question. Yeah, so d is the number of features in your raw data. So let's say, for example, in your diabetes example, right, the number of features were whatever, I don't know, 32, 64, 64, right? 64 features. So that is something that is given to you, right? And then you do polynomial expansion. Then you have the choice of applying however many functions you want to apply. So that is p. So you can choose one function, p will be 1, or you can choose 10 functions, p will be 10. Right. So essentially what you're doing is you're modifying your x and making a new input matrix like this, right? So then your prediction would look pretty much like what was here. So this is the prediction if you don't do any polynomial expansion, if you're dealing with your original data. So your new prediction in this case will become, this stays the same. So, so let's take a careful look at this one, right? So all that is happening here is because we have converted our data. So earlier we were working with raw data, but now since our x has become phi, so now instead of x we write phi here, phi, and instead of your x star, which was your new test object, you will have to convert that also into a polynomial expansion, of course, right? So I write it like this. I'm applying all these functions to this new data object, right? So, so this looks pretty similar, right? The point that I'm trying to make here is that now if you look at each one of these entries, right? So if this matrix, in this matrix, this is phi t, each entry is the inner product of those two elements, right? So each entry is actually just an inner product between phi of x, xi, and xj, right? So, so that's the point. So what's happening here is that now, and for phi times this part, right? This will be just, each entry will be an inner product between xi, x star, right? Any questions? Yeah, go ahead. One of you. Right. Okay. Yeah. Yeah. So the question is, right now what we say is that you have these p functions, right? And they apply to the entire vector. Now it's your choice, right? Now the form of this could be anything. You might use all of your d features, or you might just choose one of the features and apply it to that. So what you're doing in problem 5 is a special case where I'm saying that phi of 1, so essentially what we're saying is that phi 1 of x is actually just x3 raised to power 0, right? So that's a special case, but you could have made it x1 raised to 0 plus x2 raised to 0. So because that the choice is yours, it's you're designing it. Yeah. I'm sorry, can you say it again? Right. Right. Oh, no, no, no. So actually, these each one of these functions are returning a scalar. So it's, so this, when you apply each function, right? Uh, each one of them is a scalar value. So you get a vector. So at the end, so it's up to you whatever functions you choose, and you'll get a whole array. So the whole vector of new features, right? So this is what you get, right? So what I'm trying to say here is that even when you do polynomial expansion, in the end, you end up computing this, right? The inner product between the new feature space, right? Uh, so keep that in mind, and then I'm going to move to the next point. So that's the idea here. That's what I said. So then what happens is that what kernel methods do is they say, hey, if everything is essentially trying to compute a dot product between your features, between your raw features or your new features, how about directly using functions that compute some similarity? Right? So instead of explicitly, so here what is happening is you are explicitly mapping your each data point into a new space, right? So each data object was in this d-dimensional space, and then you mapped it into a p-dimensional space, right? But and then you computed the similarity function between each pair, right? So what kernel methods do is they say, let's skip the step where you are explicitly mapping them into a new space. How about we directly apply a function, all right, that computes the similarity. So for example, try to see if I have a good example here. Right. So for example, if you had done this, let's say you were doing this, you were trying to say that this is your x, right? And you were replacing x by these functions. So let's say x was in two dimensions, so d is 2. So each x is nothing but x1 comma x2, right? There are only two attributes. Let's say you replace it by x1 square, x2 square, and under root x1 x2. All right. Can you see? Yeah. So so this is your phi1, this is your phi2, and this is phi3, right? So you take each object and you replace it by three of these, right? So you can, to do this nonlinear mapping, you can do the long process where you explicitly compute, first compute your big matrix phi, where you take each data object and multiply them, right? And you get that. And then compute phi transpose, right? And I'm going to, from now on, represented with this matrix K. Okay, so K is n cross n, which such that every entry in K is the inner product between these two, right? And we also compute the x star, right? So this is to get the prediction, right? So let's see here. So remember, when you're doing this nonlinear mapping, you compute this and this, right? So I'm going to represent this or denote this with a capital K, and I'm going to denote this part as a K star. K star, it's a small k, like this. K star is n cross 1, because that's the inner product between your every training point and your new data object, right? So this. This is the long process where you explicitly first map it into a new dimension space, p dimension space, and then compute this, or directly compute k and k star by applying a function that we call a kernel function. Okay, so we can say that k of ij will be what will be k of ij? I think it's going to be, second. Right. Right. Yeah, I'm going to put a, what am I going to put here? Okay, yeah. So let's say our x is not, the third one is root 2 x1 x2. So I'm mapping each data object into this three-dimensional space. Initially they were d equal to 2, now p is equal to 3, right? So, or we can directly compute this, because if I do this, if I take my xi and take a dot product with xj, right? What will that be? So, sorry, phi of xi and phi of xj, right? So this, of course, is these three. So this will be xi1 square, xi2 square, root 2 xi1 xi2, this vector, right? And then I'm going to take a transpose. Okay, this should be written in that format, sorry. And then this with this is xj1 square, xj2 square, root 2 xj1 xj2, right? Because I'm going to compute the dot product in the new space. So if I do this, what it will look like is, it essentially will look like this eventually: xi minus xj square, which is a Euclidean square of the Euclidean distance between these two vectors. I'm just skipping some of the steps, but when you multiply these and get it, this will look like this, right? So what's happening here is that so this is short process. So one way to do the linear regression in this new space is that you explicitly compute these matrices, right? The new feature space, and then compute the dot product by taking every vector and multiplying it, or using a function, okay? Using a function k, which is this. Using a function k and building your k matrix directly. So we build k directly, all right? I just a little confused here myself. So any questions? This is a very important part. Yeah, go ahead. Well, it'll be symmetric, but yeah, it's one is xi, one is xj. I don't know how to write j. Yeah. So yeah. Uh, Actually, no. Right. I think let me try it again. Yeah. I see why I've led you astray here. Okay. So let's go again. So this is the example, right? We assume that d is uh, 2, right? Which means that each data object, so xi is actually xi1 comma xi2. It has two attributes, right? And each xj is also xj1, xj2, and so on, right? So that is your data point. That is your data matrix. Now you want to you want to do this polynomial expansion, okay? One specific form of polynomial expansion where we say assume p equal to 3 and phi of 1. P equal to 3 means you have three basis functions that you're using. So phi of 1 is going to do x. So this function is going to apply on on your x, right? So let's say it's applying on xi. So this is xi1 square. Phi of 2 is xi2 square, and phi of 3 is xi is just to root 2 xi1 xi2. Okay, so this is what we have come up with just out of my head, right? So, and we can do anything like that, which means that now so if I want to do regression in this new space, right? So if I want to first, so what I would do is, so long process is, first step 1, compute the phi matrix. Okay, so the phi matrix is what? In the phi matrix, you will take each object in your data, your axis, right? Where this axis is basically each xi, xj, all in this row, and then you'll convert it into phi, which will be, so this is nd and this is n cross p, right? So what you would do is you'll apply these three functions on each of these two values. D is equal to 2, of course, and then you get three values, and you do it for every one of them, right? And then step number 2 is compute phi transpose, because that's what you need. And phi transpose is essentially you're multiplying this matrix by the transpose of itself, right? Then the third one is compute the new data point, the phi x star, which is just three values, right? You take your x star and apply these three. And the fourth is compute the whole thing, which is uh, y transpose lambda in plus inverse. You already know that, and then you also have computed this. So this is the long process to do this nonlinear regression. What will happen because of doing this modification is that you would be able to learn more complicated lines, right? In this case, actually, you would be able to learn circles because geometrically that's what the equation is, right? So this is one process. Now I will show you another way to do this. So that is we call short, right? Consider the function k, which takes two data objects in the original space, in the d-dimensional space, right? And let's say this function is nothing but xi minus xj and the square of their modulo, right? So this is just the Euclidean distance, square of Euclidean distance between these two vectors, right? And let k be a matrix such that k of ij, so the ijth entry of this matrix is equal to this function, is k xi comma xj, right? And then we say let k star be a vector such that k star of I is this function k times function applied to k xi and x star. This is your new data object, right? So what happens now is that this is nothing but this. K is the same as, and k star is nothing but your phi x star. So this is nothing but this part, and this is nothing but this part. So the difference between these two, because you can still, now you can do the same thing. The difference is that you have avoided these two steps, right? Because you didn't, well, actually, you had avoided these three steps. You didn't really have to do this mapping because you had a function here that if you applied that function to your original data objects, you would have gotten the same k which you would have gotten if you had done this multiple steps, all right? Skipping the steps is not the main benefit here. The main benefit here is that now if you had a similarity function between your objects, you can use those to do this nonlinear regression, because you don't really need your x's in a vector space. You don't need them to be in a d-dimensional space. As long as you have a function that you can use to compute the similarity, right? So now these x's can be images, or two flowers, or trees, or graphs. Tree means mathematical tree, of course. So the the function k is important. This is what we call a kernel function. It takes two objects as inputs, right? And the matrix k, which is, in if you had done explicit mapping, this corresponds to phi transpose, is called the kernel matrix. Sometimes we also call it the Gram matrix, which I have no clue why, but I think it comes from more mathematical area. But this k is nothing but a matrix that is built by applying this function k to every pair of objects. All right. So any questions about that? Yes. Right. So that's a good question. So here, so the question is, are there any constraints on what function this should be? And the answer is yes, it needs to be, and we'll come to that. But if you look here, right, here what I had done was I had chosen some mapping, right? And I had chosen this function, which is here. And it turned out that this function is equivalent to this mapping, right? Which is here because we have chosen that. But in reality, in practice, you can have any function. So now we can we can design functions that operate on any type of objects, right? So you can have a function which takes a document I comma document j, or function that takes string I string j, and so on, right? However, it's not like you can come up with any function, right? So you can apply a function, but it needs to have certain properties. And the properties are typically not imposed on the function, but on the matrix that comes out of that. So this kernel matrix needs to have certain nice properties, because what will eventually happen is that this kernel matrix, right? So now if you think of it, so now the prediction would be y transpose lambda in plus k inverse k star, right? So if you have a training data in which you have some objects, bunch of objects, uh, and you have their corresponding labels or corresponding target values, then you can create this kernel matrix by applying this function on each pair, and you can create this kernel vector by applying, you know, the new object and the training objects, right? However, you need to make sure that this k is well behaved, because if this k is anything, you might not be able to compute this inverse, right? So there are certain properties that needs to be, and I'll come to those, that this function needs to follow. Okay, so we will talk about that soon. Any other questions? This is a very important part in this whole kernel methods area. All right, so let's go here. All right. So I talked about all of this, right? I said that you can replace your dot product with a function, and then the function lets you compute the regression without explicitly mapping. So this is what we call the kernel regression. So now you can come up with arbitrary functions and apply it, right? So then comes the question, how do you construct a kernel, right? So this is, of course, the simplest kernel that we have talked about. Which is just a, so here you're actually not mapping anything. This is just the dot product, but you can start with, so one thing is you can start with a basis function, but that's not what you want. You can actually do a direct design, but the main thing is that this gram matrix or the kernel matrix need to be positive semi-definite. All right, so I'm assuming you are familiar with what a positive semi-definite matrix is. A positive semi-definite matrix is a matrix which is equivalent to a non-negative number. So we talk about non-negative numbers, which means they need to be greater than 0. So in the same case, you have a notion of a positive semi-definite such that which is kind of equivalent to a non-negative matrix in some sense. There's also something called a positive definite matrix, which means it's a strictly positive number, right? So there are some properties of a positive semi-definite matrix. So something is a positive semi-definite matrix if so this is just a side discussion. I'm assuming you are familiar with that, right? Positive semi-definite matrix, or a PSD, is a matrix X, or a matrix such that uh, what is it? A minus, no, X transpose A is always greater than equal to 0 for all x's, right? Is that right? Anyone can confirm this? But basically, for any vector, a matrix X is positive semi-definite if for any vector, if you multiply X transpose with that matrix and then X, then this value, this will always be a scalar, right? Because here, this is going to be X is whatever. Let's say A is n cross n, right? So then this will be n cross 1. So this value will be a number. So if this is always greater than equal to 0, then it is a positive semi-definite matrix. If X transpose AX is strictly greater than 0, then it is a um, positive definite matrix, right? Right. Why do we care about these? Is because if something is positive definite, then you can always construct its you can always compute its inverse, right? If it is positive semi-definite, then because we are adding, so what happens is that in the case of this kernel methods, right, because we are adding this extra quantity, so this whole thing will always be positive definite if k is positive semi-definite. That you can verify very easily. But the main point is that you cannot arbitrarily choose any function. You need to choose functions such that the resulting kernel matrix is positive semi-definite. Then that is an appropriate function. Okay, and also k should be symmetric, which means that k of xi comma xj should be same as k of xj comma xi. So these are the properties that you need to hold. Now, so if you want to create a function, right, what would you do? You will come up with a function, right, any function. So k of x, here I'm doing x bar, but basically xi xj. Let's say you say that k xi comma xj is sine of xi plus cos of xj, just for the sake of argument. So now how do you verify, or how do you show that it is a valid kernel? You will have to prove that the resulting covariance matrix is positive semi-definite. In some cases it is easy to do, in some cases it is harder, right? But another interesting property is what you can do is you can use some building blocks. So let's say you already know that there is this kernel function which is valid, which means that the resulting kernel matrix or the gram matrix will be PSD. Then a new function, which is essentially just a scalar product of, I mean, a scalar multiplied with that, will also be PSD. So these are just general rules which are true, right? If you have a function, you can multiply it with this matrix, it would still be valid kernel. You can do a polynomial expansion of some known kernel matrix, then it will also be polynomial. So these are all these. You can combine two, you can multiply them, you can do some kind of a functional conversion, right? So these are the ways you can come up with new kernel functions by taking some old valid kernel functions and then combining them. Yes. No, so f is a function that is applied to x. Um, then it won't hold. You're right. So there needs to be some. I'll verify this. There needs to be some constraints on f as well. But the main point here is that there are a lot of kernel functions already there. Okay, like these ones, which people have already gone through the process of proving that they are valid kernels. And typically, what we do as machine learning researchers is that we tend to use them, right? But if you do need to come up with a new function, then you have to go through the process of proving that it is a valid kernel function, which means that either you go through the first principles, which means you create the gram matrix and then you show it will always be PSD, or you can see if you can construct the new function as some combination of your existing functions and then show that yes, it is valid. All right, but the main point is that now you have the ability to construct linear regression for any type of inputs as long as you have some similarity function that can be applied to a pair of objects. Okay, any questions so far? All right. So that is one reason we do kernel functions, and another reason is because we want to do nonlinear mapping, right? So we will talk more about them next time, but today I want to sort of end with a small demonstration of why this is useful, right? So let's say this is your data set, all right? So this data set has only one attribute. It is on a number line, okay? And there are two types. So this x-axis is your feature, and these are your labels. So some of them are pluses and some of them are circles, right? Now let's say you want to learn a line that this, or you want to learn a classifier that distinguishes between the two, right? Now if you learn a logistic regression classifier, you would never be able to learn a line, right? Because if you draw a line, now your line will have to be in one dimensional as well. Now that line, of course, you can draw these vertical lines, but you can never draw one line that will put all the red in one corner and all the blues in one, because the data is not linearly separable, right? But what you can do is you can map this data into a higher order space, which is the motivation, one motivation behind kernel functions. So let's say this is our basis expansion. So you're going to replace x by x and x square. Okay. So what happens in that case is that now in 2D space your data looks like this, right? Because what you did was you took each data point here and then you replaced it with, so one of the attribute becomes the same x and one of them becomes x squared, right? Simple polynomial expansion. Now here you can see that you can draw a straight line like this, which distinguishes between these 2 points, right? That's easy. Now what happens is, if I bring this data back into one-dimensional space, right? Because the data was originally in one-dimensional space. So in one-dimensional space, your data would be like this, but this line would now start looking like a curve, right? And that's just, you can follow these steps. But essentially what's happening here is that you are mapping your data into higher order space, right? Because in your original lower order space it was not possible to draw a line, and then when you go into higher order space, there the data is indeed linearly separable, so you can draw a line. And then when you bring it back, because the raw data was in one dimensional space, the line becomes a curve, right? So behind this kernel mapping, you go into higher dimensional space where data, you can draw a line, then you bring it back. All right. A quick example is for the 2D case. So this we have seen a lot in the past, right? Again, in this example, it is hard to draw a line, right? This data is never linearly separable. But if I go up in, so here what I do is, now I have not talked about RBF kernel, but there's one kernel that we will look at on Wednesday. If you do the mapping in that dimensional space and you bring it back, it is able to learn these curves. So actually this RBF kernel, what it does is it maps the data into an infinite dimensional space and tries to draw a line there. And then when it brings it back, the line becomes a curve. All right. So next class, we will look at more about RBF, or radial basis function kernel. And we will also talk about why it actually maps it into infinite space and then how it comes back. All right. Any questions so far?